Hello and welcome to the Distributed Systems class. In this lecture we will discuss blockchains. Let me start by saying that we will be considering blockchains through the lens of distributed computing. We won't be addressing many other interesting topics that people are considering in the context of blockchain, such as economical and financial implications or applications that can be built on top of blockchain, different type of coins, and so forth. So distributed computing and distributed algorithms are fundamental technological underpinnings of blockchain. And for us, it's going to be a case study pulling together all different topics that we have studied in this course. That would include basic principles, algorithms, models, and abstractions. Understanding the fundamental blockchain technology is absolutely essential, given that there is so much misunderstanding going on in this space, with people tending to attribute all kind of magical, mysterious features to the blockchain. So understanding fundamentals of how it is built will enable you to make your own independent judgment with respect to its capabilities and limitations. So here's how we're going to proceed. We'll start from the basic question, what is a blockchain? We'll then continue to discuss the concept of decentralized trust, which is the core idea and motivation underlying the blockchain. This will bring us to the question who is allowed to vote, because a voting scheme is fundamental to realizing this concept of decentralized trust. Finally, we will see how these concepts of voting and decentralized trust can be realized computationally in a distributed system. And we will see that the way to do it is going to be to employ the notions of consensus and Byzantine fault tolerance that we are already familiar with. Before I continue, I would like to give credit to my prominent colleagues, Itai Abraham from VMware Research and Professor Maurice Herlihy from Brown University in the US, who let me incorporate their materials in this lecture. There are excellent video recordings on YouTube of both these researchers talking on various topics in the context of blockchain. I highly recommend that you watch this if you are interested in this area. You can find the links to this on the last slide. So what is a blockchain? Essentially, at the basic level, blockchain is just an implementation of the abstraction of distributed ledger. And what is a distributed ledger? It is just a sequential list of things that happened. And this list is a append-only list of events. That means that we can't go back in time and modify things that happened before and recorded in the ledger. We can only append new events to this ledger. So these events are not necessarily just financial. So it's not just, for example, paying to parties or withdrawing money or transferring money between accounts. So that could also record arbitrary transactions and can implement arbitrary state machine. Okay, so as we discussed, an arbitrary service can be modeled as state machine understanding certain commands that can change the state of this service. And distributed ledger is basically just a script that can be executed by the state machine in order to achieve the desired outcome, to get to the desired state. So what is important in the context of distributed ledger is that it is replicated. It means that everyone can independently verify its content. And for that, it is absolutely critical that everyone agrees on its content. So it must be identical everywhere. And the way to achieve it, not surprisingly, is to use the tools that we discussed, such as consensus, total order broadcast, and state machine replication, which are enabled through total order broadcast and consensus. And it is important that this ledger is tamper-proof. So malicious parties can't mess around with it and say change its content for some of the parties. And this requirement of being tamper-proof leads us naturally to the use of this concept of Byzantine fault tolerance, or BFT, that we are already familiar with. So the origins of blockchain can be traced to the ideas of simulating physical cash, such as banknotes and coins, by means of digital tokens referred to as digital cash. And as we discussed in the context of the consensus problem, the main course or main central problem with implementing digital cash system is how we avoid double spending. And double spending is basically about the situations when the same coin is used more than once to, for example, pay to different parties, or as is shown here on this diagram, to pay to different merchants. So here the same coin, and you can see that this is indeed the same coin by inspecting its identifier, is being used to pay to the coffee seller for the cup of Starbucks and to the pizza place for pizza. So Bitcoin is by no means the first attempt to implement digital cash. One of the early examples can be traced back as far as 1989, and it was the startup called DigiCash by the prominent security researcher David Chaum. And the way Chaum addressed the problem of double spending was to introduce this server called Mint. And Mint would basically be a secure database that stored the mappings from user accounts to the coins being held by those users. And so in order to pay to a merchant for a pizza, what user will do, it will first contact Mint and possibly deposit a coin to their account to the Mint, and then they will instruct the Mint to pay the required amount to the merchant, and Mint will then check if it can actually do this, if this user has enough coins, and if it is not trying to spend the same coin twice. Okay, so this is the concept of the Mint, but the problem, of course, is that Mint is a centralized entity, and we have to trust the Mint. And so avoiding the need to place the trust into this centralized authority was the main goal of Bitcoin and its mysterious founder Satoshi Nakamoto. So the essence of the solution was to replace the Mint with a distributed ledger that is replicated across all the parties participating in the system, and therefore can be independently verified by each party without the need to contact any kind of centralized authority. And then with that ledger, it is actually quite simple to verify if the user has not already spent the coin that it is trying to use at the moment. And what is needed is just basically to just go back and in this ledger and see if the same user has spent this coin already or not. And the coin is only accepted if it was not already spent. So here is the quote from the original Bitcoin paper by Nakamoto summarizing this approach. Transactions must be publicly announced, and we need a system for participants to agree on a single history of the order in which they are received. So this single history of the order on which everyone has to agree, is nothing else but a distributed ledger. So the main tenet of the Bitcoin paper was that the centralized trust is a bad thing and it needs to be replaced with the decentralized trust. But what is decentralized trust? So that's the first question we have to ask. And then we can see how we can potentially implement decentralized trust by means of a computing system. So to define decentralized trust more precisely, let's first talk about what centralized trust is. So here's one definition. So centralized trust system is the one in which one entity makes at least one important decision. And the examples of centralized trust systems are abundant. So these include financial systems such as Visa and MasterCard, and big technology company such as Facebook, Amazon, Apple, Netflix, and Google, which are collectively known as FANG, or government. And this is not accidental that many systems we are familiar with and work with on everyday basis are centralized. And this is simply because they are cheaper, more efficient to build, maintain, and control. So for that reason, many modern distributed systems actually designed with the centralized trust in mind. So their design follows this kind of the idea that we have a centralized authority. So, and we can think of many examples, such as transaction coordinators, consensus leaders, or primary backup systems, and so forth. So they all have these special entities into which we place higher trust than on the rest of the system. Okay, so but centralized trust is problematic, and as we all know, centralization can be dangerous over time, in particular over centralization, as it leads to diminished security. So we actually need to trust that that centralized entity is doing enough in order to ensure that the data we entrusted with is properly protected, anonymized, that the sensitive information is not disclosed or leaked, and so forth. Can also diminish its availability. So if the centralized system becomes unavailable, for example, due to failures, then all services depending on this system can't work. So you can imagine what happens if, for example, Netflix goes down or Amazon goes down, and these things actually happened in the past. So another type of risks doesn't have anything to do with technology, but basically with the kind of political or societal implications, such as corruption. So the centralized authority is easier to corrupt, monopolization, unfair competition, compromised privacy, we already discussed, and so forth. And so the vision was to use this concept of distributed ledger to build a world where corporations and government can't control what we do. And so this is how Bitcoin came about. So this is the first page of the famous Bitcoin white paper by Satoshi Nakamoto. And here's the another quote from this paper. We're actually going to use a number of quotes from this paper because they're kind of informative and allow us to gain insight into the actual motivating factors underlying this very influential system. So here's the quote related to this problem with centralized authority, is that what is needed is an electronic payment system based on cryptographic proof instead of trust, allowing any willing parties to transact directly with each other without the need for a trusted third party. So now we can talk by contrast what decentralized trust means. So in the decentralized trust system, decisions are made collectively by a group of independent agents. And they are considered more secure and trustworthy based on the premises that it is much harder to corrupt multiple parties than it is to corrupt a single party. And in particular, no small group can determine the outcome. And so if there is a small group of people or entities or parties who are become corrupted, they can't influence the outcome. So they still their power is still limited. So what is the basic way of realizing decentralized trust? So it is by voting. So decisions are being made by this mechanism of voting, and what we're going to do is determined by the votes from a majority. So majority determines the outcome. And the core premise, of course, that it is hard and expensive to corrupt 51% of the group. Okay, so it most the minority in the worst case can become corrupt, and even that is not easy. And so these concepts of voting are relatively well understood in the real world, right? So this is how democratic states and government are functioning. But the challenge is how we can take this idea of decentralized trust and voting and translate it to the world of computers, and in particular to the world of computers which are distributed and decentralized. Okay, so that was the main challenge which was first addressed by Bitcoin and described in the Bitcoin paper. And that brings me to fundamental question: who is allowed to vote? So here's an example from the real world. So if you take France as a country, so in France the voting was first introduced for adult men in 1792. This is when the French Revolution happened. So that didn't work for them too well at that point, so they then tried to reintroduce it again in 1848. So from 1848, adult men could vote in France. So then in 1944, from 1944, adult women can also vote. And in general, only citizens can vote. Okay, so this is just an example from the real world. I'm not trying to say whether this is good or bad, but this is basically what happened. And conclusion that we can, or the critical observation that we can make from this example is that determining who has the right to vote must follow strict rules, and the right to vote must be hard to come by. So in all countries today, only citizens can vote, and it is quite difficult to become a citizen for anyone who was not born in a specific country. So you see that the voting right is hard to obtain. And this is crucial for a democratic system to function, because it determines how the power is distributed. And so if we are trying to translate it back to the computing world, then we inevitably come to this problem or a challenge. So if our adversary controls all votes, or for example can easily obtain or spoof arbitrary many votes, then decentralization becomes fundamentally impossible. So here is an example of an attack against the voting system. So imagine that we have a legitimate person who casts a vote, and then adversary is somehow able to take this vote and replicate it many times, for example by assigning it to many different people. And so this is what is known in the literature as Sybil attack. And one way for that to happen is, for example, have a voting system in which the right to vote is determined based on the IP address of the host from which the voting is done. And so in this case, again quoting from the Nakamoto paper, if the majority were based on one IP address, one vote, it could be subverted by anyone able to allocate many IPs. Okay, so the name Sybil attack comes from this book Sybil, which basically describes the story of a woman who's somehow imagining herself to be many different people at once. And the name of this main character just happened to be Sybil, so this is how this attack became known as Sybil attack. With this in mind, let's discuss various mechanisms that can be used to verify if an entity has a right to vote. So the most straightforward mechanism is known as proof of membership, which basically means one member, one vote. And the membership can be, for example, in an organization or in a community, and can be proved through some sort of cryptographic certificate. The direct analogy in the real world is what we have when we vote in elections. So we have somehow to prove that basically we are citizen of a specific country. So for that we can, for example, show our citizenship certificate, such as passport or a specific voting registration document. So this is something that is basically assumed by a traditional distributed system, and this is what we have so far assumed in the algorithms that we have studied, that there is an a priori known set of n processes, and the adversary has a fixed power, such as it can corrupt at most half, or at most a minority, or at most 1/3 of the processes. So in the world of blockchain, this is also known as permissioned model, and that reflects the fact that in order to become a member of something, of the voting class or of a voting organization, you need to prove that you have permissions to do so. For example, by exhibiting a proper cryptographic certificate. So to distribute and manage the voting certificates, one will need a trusted centralized authority, such as, for example, public key infrastructure or PKI, and this is something that, as we discussed, we want to avoid. And so for that reason, the voting scheme that is used by Bitcoin is something else, and it is known as proof of work, or POW. And in its essence, it basically means the following: one CPU, one vote. So in particular, POW does not require the set of participants that have voting rights to be known in advance, and as a result this set can also change dynamically. And for that reason, this is also known as a permissionless model. So that means that you don't need to have any special permissions from the third party in order to take part in voting scheme. But as we discussed, we need something which is hard to come by in order to prove our right to vote. So this something hard to come by in the Bitcoin proof of work is the CPU power. You need to actually prove your right to vote by demonstrating that you have a CPU, and you do this by solving a moderately hard cryptographic puzzle. And by demonstrating solution to this puzzle, you prove that you actually have a CPU and therefore you have the right to vote. So doing this is expensive, and some people compare the proof of work to the proof of burning a 10-pound note. So the basic assumption in the Bitcoin proof of work scheme is that adversary controls less than 50% of total CPU power. And again, the quote from the Nakamoto paper: the system is secure as long as honest nodes collectively control more CPU power than any cooperating group of attacker nodes. Since proof of work is so expensive and as a result may negatively affect the system performance, such as transaction throughput, people also thought of alternatives, and one such alternative is proof of stake, or POS, which is recently becoming more and more popular. So proof of stake basically means that one coin is allocated one vote. So the way a party can obtain this coin is external to the system, so that is normally some form of digital cash. And then the total amount of stake is the sum of all the stakes that different participants have, and the idea is to ensure that the voting power allocated to each party is proportional to the amount of stake contributed by that party. So one advantage of using POS, in addition to the decreased costs, is that it also allows punishing parties that misbehave by slashing their stake. So it's something that is known as stake slashing in the blockchain jargon. And similarly to the proof of work or other systems, the adversary power is expressed in the fraction of votes that it can control. And in the case of proof of stake system, this is as the assumption is that adversary controls less than 50% of the total stake. So here are some other voting schemes that have been proposed as alternatives to the proof of work. So one such scheme is called proof of space, and space here refers to the space in the computer memory, of course. And there a vote is allocated per 1 gigabyte of space available. So other work include proof of space-time, proof of replication, and so on and so forth. So all these schemes come along with their new associated cryptographic puzzles, and they're quite interesting, though they are at the moment they mainly subject of research papers and not yet evaluated in practical systems. So if you're interested, you can find information by looking up relevant papers. So of course the important question to ask is whether these schemes actually guarantee a fair distribution of voting power. And this question has been asked many times, and there is a lot of exciting research in this space. For example, One of the first papers, kind of groundbreaking paper, established that the mining in Bitcoin is not actually fair, and there is actually possible to mount an attack which will deviate from the fair distribution of mining capabilities. And another paper investigated the degree of decentralization in the existing blockchain networks such as Bitcoin and Ethereum, and they actually found that these networks are much more centralized than we would like to think. So we won't have time in this lecture to cover any of this. We probably need a separate lecture or a couple of lectures just to discuss this topic. But if you're interested, again, you can find information in the research papers. So important observation is that a scheme used for maintaining voting rights is in general orthogonal to the consensus protocol used for maintaining the distributed ledger. So in this table you can see summary of most prominent blockchain systems existing today. So here on the left column, in the middle column you can see the voting rights scheme used by these systems, and in the third column the specific consensus protocols. So you can see that you can mix and match in any way you like. So for example, Nakamoto Consensus can be used with both proof of work and proof of stake. Then we have something else which is called PBFT, or practical Byzantine fault tolerance, and this is one of the most versatile protocols. And as we will see, its original implementation was designed for these traditional proof of membership systems, but then it was extended by the use of a committee to other systems that support proof of work or proof of stake, or even completely different voting scheme which is based on trust. So this is in the system called Stellar. So we'll now proceed with discussing different consensus algorithms being used in the blockchain, and so this will be what we're gonna do in the remainder of this lecture. And so we will focus particularly on two representatives. So one is the Nakamoto Consensus and the other one is PBFT. And then we also discuss a little bit how PBFT can be used with the committee to combine a fairness of proof of work or a proof of stake with more determinism guaranteed by the basic PBFT, which works with the proof of membership. So before proceeding with presenting the actual consensus protocols, let's first set the scene and discuss how consensus for blockchain is basically used for building distributed ledger. So as we said, the ledger is distributed and replicated at the nodes. So the nodes are the participants in the system. So nodes are typically organized into a random peer-to-peer overlay network. And it is called overlay network because this is an application level network. That means that the system itself, the blockchain system itself, is the one responsible for maintaining the actual connections between the different nodes. This is not the network, not a physical network, not the network established at the level of TCP/IP, for example. So there are typically two types of nodes. So one type of node is a client node. So those are just the users of the system. They don't participate in the actual consensus. And the other types of nodes is called miners or full nodes. So these nodes are full participants in the system, so they can in particular be also clients, but they also participate in the consensus protocol, which is sometimes referred as mining, because you are trying to agree or mine the next block that are going to be appended to the blockchain. So clients are those who create transactions. So for example, buy or sell a coin or any asset in general, or reserve an asset, or you can also place an asset into escrow, and so on and so forth. So this is for a general purpose blockchain such as Ethereum, and the blockchain such as Bitcoin, all transactions are restricted to basically just paying cash between different parties. So clients send this transaction to miners, and they use this overlay network that we mentioned in order to do this. And then miners are those who actually batch these transactions into blocks. And then they trigger a consensus protocol to decide whose block should be the next one to be appended to the ledger. And the question, of course, is why miners are going to do this. And the answer is that in the blockchain systems, miners are incentivized to participate and follow the rules by being paid for the accepted blocks. So in the Bitcoin or Ethereum, they're being paid a fraction or fixed percentage of the transactions, which is the total value of the transactions in a specific block. So notice this is why this system is actually called blockchain. So this is not for any particular or mystical reason. It is just because working at the granularity of individual transactions is more expensive than actually batching transactions into bigger chunks, such as blocks, and then agreeing on many transactions in parallel by basically running consensus over these blocks. So as a result, the ledger is actually internally comprising these blocks of transactions. So it is a append-only list of blocks, and this is why it is called blockchain. So the problem that is being solved by the miners in order to determine which block needs to go next into the blockchain is nothing else than the consensus problem we are already familiar with. So we discussed consensus problem in the context of crash fault tolerance systems, and in the context of blockchain, we need to be tamper-proof, and therefore we need to support a higher degree of protection, and in particular we have to be able to tolerate arbitrary or Byzantine failures. But otherwise, as you will see, this is basically the same problem of distributed consensus that we have discussed at length in class. So first, one note on terminology. So in the blockchain space, what we called proposed values in the classical consensus are of course blocks. So this is the consensus over blocks. So the blocks are the values that are being proposed and decided. Processes are referred to as miners or full nodes, as we discussed. So basically the nodes are used instead of processes. Then the notion of deciding a value will be committing a block, and what we call the correct process, so the process that never suffers any failures throughout the lifetime of the algorithm, is what is called in blockchain honest miner. So the node that plays by the rules and is not trying to deliberately subvert the protocol. So in terms of properties, those are very similar to the properties of consensus we already discussed. So termination requires that all correct processes eventually decide. So this is what ensures that blockchain continues to grow. Agreement requires that no two correct processes decide differently. So this is what ensures that the copies of blockchain remain consistent across different distributed nodes. Now, the notion of validity is a little bit different in the context of blockchain from those used in classical systems. So in the classical Byzantine Consensus, validity requires that if all correct processes propose the same value, V, then any correct process that must decide V, decide this value that was proposed. So the validity notion in blockchain is related to this requirement of fairness that we have already discussed. And for that reason, it is often referred to not as validity, but something like chain quality or censorship freedom or just fairness. And there are many different definitions, but at the most basic level, basically are asking that the fraction of blocks committed by every honest miner is proportional to its voting power. So for example, it's impossible for one of the miners to commit much more blocks than the voting power that was assigned to that miner, because in that case we deviate from this requirement of decentralization. So basically there is a miner or a group of miners that have a disproportional power and, for example, can censor the transactions that are accepted into the blockchain. So this is the definition of Byzantine Consensus, and in particular in the context of blockchain. So now let's look at the actual algorithms, and the first algorithm we're going to look at is Nakamoto Consensus. So this is the algorithm that was proposed in the original Bitcoin white paper by this mysterious character Satoshi Nakamoto. So as we did with other algorithms that we discussed in this class, let's first look at the data structure and state that is maintained by each node, capital P, participating in the Nakamoto Consensus protocol. So the main data structure is, of course, the local chain replica, and it looks like this. So there is a portion which is a linear one, so it is here in red. So those are committed blocks, and the committed blocks together they constitute what is known as main chain. So the chain always bootstrapped with a genesis block, which is known to every participant in the system. So it is a fixed block that we denote here as B0. So the position of a block in blockchain, or a sequence number, if you like, is something called height. So the genesis block has the height of 0, then the next block after the genesis block is at height 1, and so on and so forth. The linkage between consecutive pairs of blocks is established by means of hashing. So actually every arrow in this diagram represents the fact that the block at the origin of the arrow has a hash of the entire content of the block, which is the destination of the arrow, as a part of its payload. And this is a particularly strong type of hashing. So this is known as SHA-256 standards, which is one of the secure hash standards. And this use of hashes is important because it basically prevents the attacker from coming up with an alternative chain. So in the blockchain, the genesis block is fixed, so it's known to everyone, and then every subsequent block will be the hash of the will include the hash of the previous one, and so the entire hash can be reconstructed from the genesis block and independently validated by everyone. So if instead of hashes we just used the heights of the blocks, then adversary can or attacker can very easily construct an alternative chain by basically assigning these heights to the blocks that it is going to produce instead of the actual blocks that are being mined. So the use of hashes prevents this possibility. So the blocks outside the main chain may not necessarily be organized into this nice linear structure. So in particular, a node may be uncertain which block must occupy a specific height. So for example, this node P still considering two candidate blocks for the height 5. And there are 3 candidate blocks for the height 6 and only 1 candidate block for height 7. So if certain heights have multiple candidate blocks, then this is known as fork. So in this picture we have 2 forks, so this is one fork and this is another fork. And it is the responsibility of Nakamoto Consensus to ensure that eventually only one block is selected for every height. So once that happens, then the selected block is incorporated into the main chain and the other candidates are discarded. So we'll talk how this is done exactly in the next few slides when we dive into the Nakamoto Consensus. So in terms of the terminology, these alternative histories that are formed by these multiple candidates or forks are referred to as secondary chains. So secondary chain always starts from the main chain and then it follows the forks. So here is one example of a secondary chain, and in this picture we have 3 secondary chains. So another chain is formed by taking all these yellow blocks and then the main chain blocks, and the third one is by starting from this blue block and then following through this green block and then the rest of the main chain. There could also be blocks for which we not yet received the preceding blocks, but those blocks are considered to be valid blocks. And how we determine if the block is valid, we'll discuss in the next few slides. So these blocks are called orphan blocks. So they're not being discarded, they're being kept, and then they will be eventually incorporated into either the main chain or one of the secondary chain once their predecessors become known. So here are some additional data structure and notation that we're going to use to describe Nakamoto Consensus. So B0 to Bn is going to be the longest secondary chain of blocks known to P, to the node P. Small o is the set of transactions that are known to P but are not yet committed. So these transactions are going to be assembled into the next block and then proposed for consensus. And IPub is going to denote the P's public key. And the public key of the node is included into every mined block, as we're going to see shortly. And that is going to be used as a proof that P has actually mined the block and therefore is eligible for collecting a fee, a mining fee for that. So now we are ready to describe the actual Nakamoto Consensus algorithm, and as you gonna see, it is quite simple. So those are 3 steps for generating a decision by a specific node P we are looking at. So the first step, P will take a hash, secure hash, of the block Bn, which is the latest block on the longest chain known to the node P, as we discussed. So that basically means that the next block being mined by P is going to extend the last block on the longest chain, longest secondary chain known to the node P. And the result of this hash is going to be stored in this variable h. So h basically stands for height. Okay, so P is gonna mine a block at the highest height +1 known to P. So as I mentioned, SHA-256 is a particularly strong type of a hash function. That means that it is impossible or computationally infeasible to invert this function without actually trying all the possibilities. And 256 stands for the number of bits in the hash that is being produced. So the next step is the actual mining, and it can be described as follows. So we want to find a value of nonce such that if we take the height of the block that we want to mine plus, so this vertical line here means concatenation, so we take this hash, concatenate it with the public signature of the node, and then concatenate it with all the uncommitted transactions known to the node, and finally this nonce. Okay, so we take all of this together and then hash it and get something that is less than capital H, which is the difficulty level. Okay, so we need to find a nonce which, when substituted into this concatenation and then taking the hash of this entire thing, will produce something which is less than H. Okay, so H is a difficulty parameter which basically determines the block production rate. So the smaller the H, the harder is to find a nonce. Okay, so H can also be viewed by the number of leading zeros that needs to be in the result of evaluating this hash. Okay, so the longer the number of leading zeros, it means that H is lower, the harder it is to solve the puzzle, to find the solution for the puzzle. And because strong hash functions such as SHA-256 is computationally infeasible to invert, the only way to find this nonce is basically to exhaustively search through all the possible values of this nonce. So starting from 0, then 1, and 2, and 3, and 4, and so forth. Okay, so this is basically exponentially the computation that takes exponential time to complete. And this is what is going to demonstrate. So correctly computed nonce is going to demonstrate that the actual CPU was spent and the node that produced the decision was actually eligible to produce it. Okay, it's not eligible to vote. So once this nonce is found, so this is the long process, right? So you have to realize that this is being done in some kind of a loop here. So, but once this nonce is found, that at this point the node knows that it actually managed to mine the block. So at this point it will basically just create a message which includes the all these 4 components and broadcast it to all the nodes using the overlay network. And this data here, this concatenation of these items here, is actually what a mined block is. So then when a mined block is delivered at a node, so let's say this is a block X with this payload, what the node is going to do is going to take hash of this entire payload and compare it against the current difficulty level. So if this indeed falls below H, then we know that this is a valid node. So it actually the nonce that was mined is the right one. So it would satisfy this inequality when plugged into this hash. Then we try to see if we already have a block which this block should follow. Okay, so for that we take this H extracted from the payload and check if we already have a valid block B whose hash is equal to H. And if this is indeed the case, then we link X after this block B. Otherwise, we just add X to the orphan block. So we know that this block is valid, but we have not yet received the block which this block is following. So if the block that we have received is not valid, then we just discard it straight away. So what we have just seen is almost the entire Nakamoto Consensus protocol. So actually, you can see that it is quite a simple protocol. And it's also quite easy to get convinced that it is live. So the nodes continuously mining blocks, new blocks, so the progress is being made. And it's also fair because the number of blocks that every node will succeed to mine is roughly proportional to the amount of CPU it has, so it is proportional to its voting power, which is what we want. So the most interesting thing about Nakamoto Consensus and the most challenging to establish is why it actually satisfies agreement. So agreement in the context of Nakamoto Consensus basically means that no two honest nodes would ever somehow commit 2 different blocks at the same height. And to see this, the most important thing to notice is that in the algorithm, nodes always, or honest nodes, always choose to extend the longest chain. Okay, so this is actually captured by this quote from Nakamoto's paper, that the majority decision is represented by the longest chain, which has the greatest proof of work invested into it. And why this holds? So at the basic level, the reason is that the honest nodes have more mining power than the Byzantine nodes. So this is the basic assumption we are making about the system. So we can represent this assumption by fixing two parameters, alpha and beta, and those are going to be respective mining rates of the honest and Byzantine nodes. So alpha is the mining rate of the honest nodes, the collective mining rate, and beta is the collective mining rate of all the Byzantine nodes. And the basic assumption is then that alpha is greater than beta. So as an example, we can take alpha equal 1 block per minute and beta equal like a half block per minute. That would mean that the total mining power available to the Byzantine nodes is about the third of the total mining power in the system. So with this assumption on its own, if the mined blocks somehow instantaneously propagate to all the nodes in the system, then it is clear, since just by the virtue of this discrepancy in the mining rate, that the branch being mined by the correct nodes will be growing faster than all possible branches that can be mined by malicious nodes. But of course, this is oversimplification, and in the real network we always have some delay until a message gets propagated. So we can incorporate this delay into the analysis. So let's say we have this known upper bound on the message delay, which is this big delta. So then to ensure that all blocks, all mined blocks have enough time to propagate, so the next block being mined will be extending the longest chain, is that this interblock interval, which is the inverse of alpha, is much greater than the message delay. Okay, and how we can ensure that? So we can basically do this by tweaking this h parameter, so the blocks are not being produced at the intervals which are too small compared to the network delay. Okay, so if new blocks are mined rarely, and so if this interblock interval is much higher than network delay, then we are guaranteed that all the mining blocks will reach all the honest nodes in time, and so they will be seeing the same picture with respect to the branch which is the longest one. Okay, and this is of course assuming that, as we said, the collective mining rate of all the honest nodes is higher than the collective mining rates of all the Byzantine ones. So this is still not a complete picture, because there's another possibility for the mining rate being slowed down just by virtue of correct nodes somehow mining a block at the same height, more or less at the same time. Okay, so that could happen because mining block is a random process, so the probability of that is non-zero. And of course, the important question is how we can estimate this probability, and it turns out to be quite complicated. So recently there was this paper published, so just a 2020 paper by Lin Kren, which actually present a simplified analysis of these different probabilities. So you are welcome to have a look. But even this simplified analysis is using quite advanced material from probability theory. So just to summarize the end result of what has been shown in this paper, and is as follows. So the probability for the nodes to simultaneously mine a block at the same height is given by this formula here as a 1 minus e to the power minus alpha times delta. And this is assuming that the block mining is a Poisson process. So the Poisson process basically means that the time between consecutive successful block minings is exponentially distributed. So for those of you who knows exponential distribution, should not be surprised by this power here. So alpha times delta is basically the average number of blocks mined in the unit of time. So then, under our assumption that we mentioned before, that the inter-block interval is much higher than the network delay, this quantity here is basically very close to zero. So, for example, if we take these mining rates that we used before, like 1 for honest nodes and half for Byzantine nodes, then and the message delay, say, of 5 seconds, then we get that this probability of slowdown because of the simultaneous mining is approximately 0.08, which is very small. So we are now ready to formulate the actual rule for committing blocks in Nakamoto Consensus. And the basic idea, as we discussed in the previous slide, is that from the perspective of agreement, it is always safe to commit the blocks from the longest chain. Okay, so the precise rule is formulated in the third bullet here, so we'll get to it in a minute. But first, just based on this assumption that on this rule that longest chain always wins, we can notice the following things. So first, Nakamoto Consensus is synchronous. And this is because the agreement, as we discussed, crucially depends on the knowledge of the network delay, delta. And this is because we need to tweak the difficulty level so that the blocks are not produced too frequently relative to the network delay. Okay? And agreement is a safety property, and that means that Nakamoto Consensus, safety of Nakamoto Consensus relies on the knowledge of this network delay, and it also must hold at all times in order not to violate agreement, in order to ensure that all honest nodes are extending the longest chain. And this is not the situation, for example, in Paxos protocol, which would never violate agreement, even if this delta, network delay delta, is not being met. Okay, so in Paxos, this delta is only necessary for liveness. Okay, so that's the major difference compared to the partial synchronous protocols for consensus such as Paxos. So then also, and this is something new, this is something that we have not yet seen in this class, is that agreement in Nakamoto Consensus is actually probabilistic. So far we only considered deterministic agreement properties for consensus, and in Nakamoto Consensus it is not. It is probabilistic. So that means that if this delta bound actually being upheld by the system, then agreement is guaranteed with high probability. So this probability is really high, as we have seen in the analysis in the previous slide, but this is still probabilistic. So this is not deterministic guarantee. And so, given this reliance on synchrony and the probabilistic nature of Nakamoto Consensus, there are additional steps that have been taken in order to safeguard against the occasional drop in the block production rate that may, for example, happen due to simultaneous mining or simultaneous forks by honest nodes, and the occasional deviations from delta, which we can't safely assume will always held in a realistic system. And so to safeguard against that, the node will only commit a block which is on the longest chain and also buried at least k blocks deep on this longest chain. Okay. So in realistic deployments, k is normally set to something like 6, and that means that given that the probability of committing mining a block not on the longest chain is quite low, so it's like 800ths, as we discussed, for some reasonable setting of the parameters alpha, beta, and delta, then committing the block that is not on the longest chain means that this event actually happened 6 times in a row, and the probability of that is indeed minuscule. So it's something like 2 times 10 to the power of -7, which we can assume that for all intents and purposes is essentially 0. So let's see how committing happens visually. So here's the situation, that here's the picture that a node may see. So this is the main chain, so all the red blocks have already been committed, and then of all the secondary chains, this chain here, the one that includes all the yellow nodes and all the red nodes, is the longest. And then we can simply count backwards from the tail of this longest chain. So this is the 6 blocks, and this is according to the rule, this is the window size which is big enough in order for this block here to be committed. And so this is what happens, and then as a result of committing this block, this fork here is going to be resolved, which means that these 3 blocks are no longer need to be kept, because we are not accepting this alternative version of events according to the rules. Okay. And so this is what happens. So this is how the chain gets rearranged after this additional block here gets committed. And so this is basically the whole protocol, and as you can see, it is very simple, which is of course the key reason why it is so successful. So now let's discuss the pros and cons of Nakamoto Consensus. So first off, probably the most important thing about Nakamoto Consensus, it is very scalable, and this is because it only uses network for propagating blocks and transactions, and that basically takes the linear number of messages per block. Okay, so for every mined block, it takes n messages to propagate it to everyone, or order n messages. It is also fair, as we discussed, because the number of blocks mined by a honest node is roughly proportional to the node's voting power, so basically to the amount of CPU power available to a node. It is also live because the chain continues to grow. So those are positives. So now to the negatives. So perhaps the most serious criticism that has been mounted against Nakamoto Consensus and Bitcoin or other protocols that use proof of work in general is the low throughput. Okay, so and this is something inherent because we can't produce blocks too frequently. because as we discussed, if you do this too frequently relative to the message delay, then there will be too many forks and the agreement can be violated. And so as a result, at the moment, the transaction rate in a Bitcoin network is something like 10 transactions per second, which is very, very low, especially if you compare that to the performance of centralized systems such as Visa, which guarantees the peak performance of 56,000 of transactions per second. Okay, so this inadequate performance actually led to was one of the factors that motivated developing voting schemes which don't depend on proof of work, such as proof of stake, for example. So another negative is that Nakamoto Consensus has a long time to finality. Okay, so this is what we've just discussed in the previous two slides. That we so the block which is being added to the chain can't be committed straight away. We first need to wait until 6 of 5 more blocks are committed on the same chain as that block, and this is actually the longest chain. So in Bitcoin it can take something like 10 minutes, which since the block mining rate is set to approximately 1 block per minute and a half. And lastly, the finality is also non-deterministic. So that means that there is a theoretical chance that a committed block will need to be rolled back. Okay, so we have seen that the chance of that to happen is indeed very low, but theoretically it could happen, and that may have some quite serious consequences for the system, because for example all transactions in the committed block, they already took effect, and some coins are being spent, and if they are rolled back and alternative transactions are committed instead of those rolled back, then we can run in all kind of problems, including double spending. So this completes our presentation of Nakamoto Consensus. So let's now continue with our review of consensus protocols for blockchain. So the next protocol we'll look at is practical Byzantine fault tolerance, or PBFT. So the PBFT protocol can be traced back first to the theoretical result by Dwork, Lynch, and Stockmeyer, so something abbreviated as DLS. And this is the paper that actually first introduced the partial synchrony model that we discussed. So it's called Consensus in the Presence of Partial Synchrony, and it was published in 1988. So then the actual PBFT, which is a practical adaptation, if you like, of this original protocol by Castro and Liskov, was first published in Symposium on Operating System Design and Implementation, which one of the top conferences in the system engineering, so OSDI in 1999. So more recently, this protocol, PBFT protocol, was optimized along many different directions, which gave rise to this new wave of optimized protocols, which basically follow the same blueprint as PBFT. And this was driven mainly by industry and the interest in blockchains. And this includes protocols such as Casper, Tendermint, Hotstuff, Algorand, SBFT. And this area is still under active development, and new protocols keep appearing, and people keep improving on along various dimensions on this original PBFT proposal. So in the nutshell, PBFT is just a generalization of Paxos for a Byzantine failure model. And just as Paxos, it assumes partial synchrony, and the overall number of processes must be greater than 3f, which means that up to 1/3 of failures can be tolerated. Okay, so the resilience is lower than the resilience in Paxos, which can tolerate a minority of failures. So for simplicity, as before, we will assume that n is exactly equal to 3f plus 1. So important thing about the basic PBFT, as we discussed, that it requires proof of membership for a voting scheme to establish the identities and the rights to vote. And this proof of membership is normally implemented via some kind of a centralized public key infrastructure, or PKI. So we'll see how the combination of PBFT with the elected committee can actually eliminate this assumption. But for the basic protocol, we're just gonna assume that we use proof of membership rules for establishing the voting rights for the nodes. So as it is, PBFT is suitable for permissioned blockchains, and it is actually was implemented as the underlying consensus engine for a Hyperledger project. So now I will briefly describe how PBFT works. We won't be covering this protocol in details because it is quite complex. We probably need a separate lecture just to discuss PBFT and its guarantees, but hopefully you'll get some idea how it works. So here we will look at a single shot consensus. So this is basically how we commit a single block, how we agree and decide on a single block in the blockchain. So in this example, we have 4 processes, so most one of them can be Byzantine. So the protocol starts by processing informing the leader of their past accepted values, if there were any. And then the leader checks the values and check if they have proper certificates. And we will discuss briefly how these certificates are formed in a few moments. And then it selects a value to propose, or if there is no any suitable values to propose, or suitable blocks to propose, it will propose some of the pending blocks known to that leader. So this is a leader-based protocol, just as it is the case for Paxos. And so these 2 phases, the first phase where everyone talks to the leader, which is called the new leader phase, and the next phase where the leader picks some value and broadcasts it to the other processes is called the pre-prepare phase. So of course a leader actually also sends the messages to itself. So for simplicity, not to clutter the picture, we won't show these self messages here. And so these 2 phases together, new leader and pre-prepare, is roughly equivalent to the prepare phase of Paxos. So the major difference is that prepare phase of Paxos is originated by the leader, and here it is the other way around. So all processes somehow learn the identity of the leader. We'll discuss how it is being done, and then send their existing proposals that are existing accepted proposals to the leader, and then leader will choose one of them or its own value. Okay, so this is roughly what happens in the prepare phase of Paxos. So now a major complication in Byzantine environment is that the leader can equivocate. So it can, in this pre-prepare phase, send different proposals to different processes. And so we need to somehow address this situation. And the way to do this is basically to use the same idea as the one used by Braca broadcast to prevent equivocation. And it's basically echo the proposal received from the leader to all other processes. Okay, so this is what happens in this prepare phase. And then in as a byproduct of echoing, every process will actually also assemble these cryptographic certificates for every value that was echoed an appropriate number of times. So if a process gets 2 f+1 echoes, that means for the same reasons that it is the case in Braca broadcast, that this value is a safe one to adopt. And in order to be able to prove this fact to other processes, the process will also attach the cryptographic certificates to these values. So each cryptographic certificate will be the properly signed proposal echoed by the sender. Okay, so that means that the size of the cryptographic certificate is something like 2f+1, which is in the order of n. So that would obviously take or order of n-square messages, so this prepare exchange. And since we have these certificates which are of size big O of n, then the total amount of information that is being exchanged in the prepare phase, or if you want total bit complexity, is actually cubic. Okay. So now, by the end of the prepare phase, all processes have identified the accepted value, which is safe, and has the proper certificates. So now this value can be committed. So this commit phase is also accomplished by a broadcast. So here every process sent this value that it chosen with the proper certificates to all the other processes. Okay, and again, a process receiving 2 f+1 copies of the same value with the proper certificate will accept this value, will actually commit this value. So this value is safe, in particular because every subsequent leader will be able to find the value that was committed before and validate that it has proper certificates. Okay, so these two prepare and commit phases together, they are essentially similar to the accept phase of Paxos. So far in our description, we just assumed the leader is fixed and everyone knows the identity of the leader. But of course, this is not enough, because a leader can also fail or behave in a Byzantine fashion, not follow the rules. Okay, so for that reason, this protocol that we that I just described can fail, and so we need some kind of a mechanism that would enable us to change the leader, so we can eventually be able to make progress, and achieve liveness, and commit a block. So the way it is done in PBFT is by using this abstraction of views. So The execution basically divided into this series of views, so they sometimes are called rounds. So in PBFT paper they are called views, and each such view has a fixed leader, basically determined by taking the view number modulo the number of processes in the system. Okay, so the views are basically consecutive integers, 1, 2, 3, and so forth, and the leader of a specific view is just the view number modulo n. Okay, so we already have seen various consensus protocols that use this notion of round, or in Paxos we have also called them ballots. So this is essentially the same situation in PBFT. So here ballots are called views, and view numbers get embedded on every message being exchanged, and they are also used in order to identify the value, the accepted value that should be chosen. So very similar to what happens in Paxos. So now the termination of the protocol is ensured by the fact that there eventually will be this what's called global stabilization time, and this is because we have a partial synchronous system, as we said. So before this global stabilization time, the system is asynchronous, and after it becomes synchronous. So no one knows when it occurs. It's just the basic assumption of the model that this GST time eventually happens, and so the termination of the protocol relies on the fact that eventually we will hit a correct leader, and after GST all messages will get through and in a timely fashion, and that would guarantee that this series of phases that we discussed would eventually terminate, and everyone will reach agreement on the block. Okay, so this is how liveness is achieved. So the last thing we need to mention is that how we actually support this abstraction of views. So that's actually quite challenging, and there has been some interesting recent work on this subject. So the main challenge is that the views before GST might be completely unsynchronized. So different processes may proceed at different speeds, and their clocks may deviate from each other arbitrarily, and messages are not guaranteed to be timely delivered, and they can also be lost. And so when we arrive at the time GST, after which everything is perfectly synchronized, the process might be in this widely different views, like you see this in the picture. And the challenge is how we can guarantee that after GST all correct processes will be synchronized in the same view. And of course, Byzantine process may disrupt this process and may act adversarially to prevent that from happening. So this is solved by this separate component, which is called synchronizer. And there were some interesting efficient protocols that have been proposed for implementing synchronizers. So we are not going to cover that, but you are welcome to explore on your own. And basically this synchronized component tells processes when they have to switch views, and once they switch view, they can deterministically know who is the leader for that view by basically taking view modulo the number of processes. And this is how they can initiate the consensus protocol that we discussed, by basically sending their previously accepted proposals to the leader of that view, and so forth. So here are some references to the implementations of the synchronizers. So the original one was proposed in this theoretical paper from 1988 by Dwork, Lynch, and Stockmeyer, and that was quite inefficient and was primarily of theoretical value. So then a more practical idea was outlined in the paper describing the hot stuff consensus protocol. So this is actually the core consensus protocol employed by the blockchain system being developed by Facebook. And then a practical implementation appeared in this Coxworth paper that was co-authored by a bunch of people from Facebook. And then there was this more recent paper that introduced synchronized called FastSync, which I myself also contributed to. So this is all about the basic PBFT. So let's briefly discuss its properties. So first, the positives. So it is a high throughput protocol, and this is because nothing basically prevents the processes if we, for example, within the synchronous period to commit transactions, commit blocks, as many as basically their resources on the network resources allow. It has deterministic finality. The finalized blocks would never be retracted later on, even with a low probability. So it is live. It guarantees to make progress if the system behaves synchronously. So it's live in the partially synchronous system. And agreement, of course, does not depend on synchrony. So this is what also we refer to as deterministic finality. So once an agreement is reached and everyone or all correct processes decide, then it can be retracted. And we also don't need synchrony for that. So we don't need to know the upper bound on the message delay. Okay, so the synchrony is only needed for liveness. So now the negatives is that the basic PBFT has low scalability. So we discussed that even in the failure-free scenarios, it would send around something like n cube amount of information, which is quite high, and that becomes significant if we grow the number of nodes. And of course, for the blockchain, we do want to have a lot of nodes in the system because that's the very essence of decentralized trust, that everyone wants to have a copy of the blockchain and participate in the block production. Okay, so we don't want to have a system where the blockchain is essentially distributed within a small group of nodes, because then this system is essentially centralized and everyone has to trust this small group of nodes. Okay, so there are some new variations of PBFT, such as hot stuff that we already mentioned, that actually reduces this failure-free complexity to being just linear by using some smart cryptographic primitives such as threshold signatures. And if you're interested, you can find more details in the hot stuff paper. So another problem is that it is fundamentally prone to censorship because a malicious leader, for example, may do everything according to the rules, but as it comes to the actual protocol, but it may actually drop some transactions as it wishes. Basically, not to include them into the block that it's going to propose. Okay, so this is what is known as censorship. So fairness may not be satisfied. And that, of course, can be mitigated by rotating the leader across multiple consensus instances. So we can use different leaders for different instances of consensus, and we can have a separate instance of consensus for each block, and we can rotate leaders between different blocks to ensure that we never stuck with the malicious leader which is going to censor the transactions. And another disadvantage, as we mentioned, that PBFT actually requires proof of membership in order to guarantee the security of voting. Okay, so we don't want arbitrary nodes to participate, and in particular we want to prevent the Sybil attack, so we can't just admit nodes to the system at will. So we need to require that from each node to prove that it can actually participate, and as we discussed, this is normally done through the public key infrastructure, which is inherently centralized. Okay, so this is another limitation. So now let's see briefly how these limitations can actually be addressed. And this is something that I called here. It's also actually known de facto as such, is PBFT with committee. And the idea in the PBFT with committee is to combine the ideas from the voting schemes such as proof of stake or proof of work in order to address these deficiencies that we just mentioned, such as closed membership and the lack of fairness. Okay, so let's see briefly how this is done. So we start from a permissionless system, such as, for example, a system with the voting scheme based on either proof of work or proof of stake. And then we use this voting right scheme to elect a committee by randomly sampling from the set of participants. And then what we do, we use Nakamoto Consensus to commit the membership of a new committee, identity of the leader, as well as the next block to propose. Okay, so we commit all this information on the blockchain maintained by Nakamoto Consensus. So when it gets committed there, it does not mean that that block is being committed. It is just the candidate block then, which we then pass to the leader of PBFT as its proposal. Okay, so that would guarantee already fairness, chain quality, and censorship freedom, and will also not restrict the participation, because we have this committee selection, and committee is being sampled from a wide set of participants which don't require any kind of admittance or permissions mechanism in order to become a part of the system. So once we have a committee and the leader and the block to propose, now we can actually execute one of the variants of PBFT consensus that we just discussed to actually achieve the finality for the decision. Okay, and by doing so, we gain all the positives of PBFT consensus, which is deterministic finality and tolerance of asynchrony. So this is essentially the way to take the best of two worlds. So one world of these permissionless systems, which use proof of work or proof of stake to establish voting rights, and Nakamoto Consensus that guarantees fairness and chain quality, and the PBFT, which guarantees deterministic finality and tolerance of asynchrony, which is not supported by the Nakamoto Consensus. or they're being supported, but probabilistically. Okay, so then if we look at the features of this combined approach, that is PBFT with committee, then we basically get ticks in all the squares. So we have high throughput by the virtue of PBFT. In particular, if we use the linear version of PBFT, such as hot stuff, we have deterministic finality, because this is what we get from PBFT. We have aliveness, which is guaranteed when the system behaves synchronously. We get agreement that does not depend on synchrony, because this is the situation in PBFT. And we also gain scalability by using one of those scalable variants of PBFT protocols, such as hot stuff, and another one is Tendermint. And we get fairness from Nakamoto Consensus, and also we don't need any specific scheme to establish voting rights, so that would work with anyone, and in particular can also support open participation, which is given by this proof of work and proof of stake or permissionless systems. So this all may sound very rosy, but in fact this is still kind of the cutting edge of research, and there's a lot of things that still needs to be done in both theory and practice to realize this vision of a blockchain consensus, which basically ticks all the boxes. So this brings us to the conclusion. So we discussed in this lecture blockchain through the lens of distributed computing. So we considered what a blockchain is, and this is basically just an append-only list of transactions. So transactions are batched into blocks, and this is why it is called blockchain. We discussed the notion of decentralized trust. This is when we take a decision collectively through some kind of a voting scheme. We discussed various mechanisms to establish voting rights, such as proof of membership, proof of work, proof of stake, and we mentioned other novel mechanisms of proof of other things. So then we put everything together and have seen how this idea of decentralized trust and decentralized decision making can be put to work through these mechanisms of consensus and Byzantine fault tolerance that we have discussed in this class. And in particular, we considered the following consensus variants: Nakamoto Consensus, PBFT, Byzantine Consensus, which is, as we said, at the basic level, just an adaptation of Paxos to Byzantine fault-tolerant environments. We discussed the pros and cons of these different approaches, and also briefly mentioned this the approach which basically combines the positives of both PBFT and Nakamoto Consensus, something called PBFT with committee. So lastly, here are some resources that you may find useful. I will put more pointers online. So that completes the lecture. Thanks for listening.